All right, so this is my problem 53 video 2 for the week 9 video explainers. So in this problem, we are given a formula for the gravitational attraction between two objects with masses m1 and m2, and they're going to be separated by a distance x. So we're given an equation for that. We'll get to that in a bit. And in the first part, we're trying to find the work that is done by gravity when the separation changes from distance x1 to x2. And we're assuming that x1 is going to be greater than the distance x2. So for the second part, we are given a situation where there is a comet passing the orbit of Mars, heading straight for the sun at a given velocity. And we're trying to find its final velocity, so the velocity of it when it crosses the orbit of Mercury. And we're gonna have to get the astronomical data just from the back of the book, because those are already proven values. And we're also given the gravitational constant. So in this first part, we know that the equation for work is equal to the force times a distance. But because force, which is mass times acceleration, we know that it's going to be a negative acceleration for gravity. So work is going to be equal to negative FD, force times distance. So going back to the equation we were giving earlier, that force for the gravitational attraction between those two objects is going to be gravitational constant G times m1, m2, the masses of those two objects, over the distance squared. But if we plug that back into the original work equation, which is we're trying to solve for, that change how much work is done when the separation of those changes from a certain distance, that x squared on the bottom ends up simplifying to just x. So we plug that back into our original equation. So negative force, which is going to be that value we just got, is going to be negative the gravitational constant times the masses of these two objects over the first distance, which is x1, and we know that's greater than the other distance, x2, and that's going to equal to the work. So that's going to be how much work is done by gravity when the separation changes from the distance x1, x2 to x2. And that's going to be used in the second part. So we can see in this diagram that a comet is passing by Mars at an initial velocity of 3.5 times 10 meters per second. And we're also given the mass of the comet, which is 1.5 times 10 to the 13th kilograms. And we are also given, we have to find, just from in the book, the orbit of Mars, the distance of that, which is 2.28 times 10 to the 8th kilometers, and the orbit of Mercury, which is 57.9 times 10 to the 6 kilometers, and that gravitational constant, which is 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. So we know that from class that work can also be, looked at as the change in the kinetic energy. So we are using that work that we got from the first part, which is the negative gravitational constant, the two masses of the object over the changes in the distances, and we'll get to which distance x variable corresponds to which orbit, equals the change in kinetic energy, which is 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. So that first distance x1 is equal to the orbit of Mars, and the other distance x2 is equal to the orbit of Mercury. So those are going to be both in kilometers, and we're given the gravitational constant. So we're going to end up plugging that back into this equation over here, and we know that the m1 is going to be the mass of the comet, and m2 is going to be the mass of the sun, because those are the two objects that we are comparing or seeing that they're interacting with in this system. And then we also are going to get the velocity of the comet. So just some quick substitution, or not substitution, just some quick simplification. We can pull out those top parts of those initial parts in the force, the gravitational attraction. So that negative gravitational constant gets pulled out, and the mass of the comet is also eliminated just due to the fact that it appears on both sides. So it makes the math a little easier for us. So that left side is going to be the simplified force, or the gravitational acceleration, and the other side is going to be the change in kinetic energies, which ends up being simplified. So all of the rest to do is just plug everything in back into the equation that we just derived. So that's going to be the gravitational constant we were given times the mass of the sun, and then the x1, x2, so the orbits of Mars and Mercury, equals the change in kinetic energy, and that initial velocity we first got of the comet, which is 3.5 times 10 to the 4th meters per second squared. And since we were solving for the final velocity, we isolate it, and we end up getting the final velocity is equal to 5.848 times 10 to the 4th meters per second. Kind of sorry this video went a little over the time limit. There was just a lot of material to cover. And this just relates to kind of how back in class, how we're just looking at systems and looking at the relationship between objects in a system, and also looking at kinetic energies. And just some of the tricky parts is knowing which distance variable corresponds to which planet, being Mars or Mercury, and just finding out a method on how to trying to find a certain variable, and we have to use different methods, and that's kind of something we've been doing the whole year. So sorry for the length once again, but thank you very much.